Hello everybody. This is going to be the final exam review part 2, which is going to cover kinematics, momentum, electrostatics, and electric circuits. And this is sort of it for the year, and I hope you use this to study. And let's get right into it. So if we start out with two-dimensional kinematics, that's what we're looking at right now. So the Grand Canyon at its deepest point is 800 meters deep. If I were to drop a rock into this part of the canyon, how long would it take to hit the bottom? And then if I threw it at an x initial velocity, 20 meters per second, where would it land? So if you remember from two-dimensional kinematics, the best thing to do to start one of these types of problems is going to be to make a chart. So let's make an XY chart. Oh boy, XY, VI, VF, A, T, D. And we know for the start of this problem, everything's going to be in the y dimension. So we know the displacement is going to be negative 800 meters. We know the acceleration is going to be negative 9.8 meters per second squared. We know the initial velocity in the y dimension is going to be 0 meters per second. And if you remember doing this back in class, the time in the y, if we can figure that out, is going to be the time in the x. And then from there we can figure out where it's going to go. So that's why we actually ask you first, how long is it going to take to hit the bottom, so you can look for it in the y, and then hopefully remember something about physics, that the time in the y is going to equal the time in the x. In the x. So the equation that I would actually use is going to be d equals VIT plus 1/2 AT squared, where d is negative 800, VI is going to be 0, and then we're going to end up with negative 4.9 t squared. And then we can divide 800 by negative 4.9, or negative 800 divided by negative 4.9. That's going to be 163. 163 equals t squared. The square root of that is going to be 12.7 seconds. So t will equal 12.7 seconds. And then once you have that for the y, that's also what it is for the x. And 12.77. I'm you know what? Let's round it up to 12.8. So it matches the answer sheet. 12.8. So if I got 12.8 seconds, I know my initial velocity in the x is 20, and because things don't speed up or slow down in the x dimension, VI and VF are the same, and we're looking for the displacement in the x now. So now we can just use V equals d over t, because that's how things work in the x dimension. This is sort of your go-to equation for the x dimension. So my velocity is 20, my displacement is what I'm looking for, and my time is 12.8 seconds, so 20 times 12.8 should give me an answer of displacement of 256 meters away. So I hope that helps. Let's move on to number 2. Ball's thrown 35 degrees above the horizontal at a speed of 35 meters per second. Where's it going to land? So once upon a time we talked about triangles, and I'm giving you at this point one. Actually, let's make it a little bigger so we can actually write around it. So 35 degrees above the horizontal. Good enough. So that's 35 degrees, 35 meters per second. And be sure you're in degree mode to answer this question. And so now we can make a chart. VI, VF, AT, D. And I hope that you remember when we're dealing with two-dimensional projectile motion, the acceleration in the x is 0, the acceleration in the y is negative 9.8. But this 35 doesn't go into either the x or the y. What goes into the x is going to be the x component of that 35, and the y is going to be the y component of that 35. And to figure that out, it's going to be 35 cosine 35 degrees, and for the y it's going to be 35 times the sine of 35 degrees. So this comes from the actual velocity, this comes from the angle you're launching it at. And if you play your cards right, you should end up with 28.7 meters per second in the x, and because it doesn't speed up or slow down in the x, it's going to be the same. And in the y dimension, it's going to be 21 or 20.1 meters per second in the y. But that's going up. And what we need to also remember is how fast it's going when it comes back down. And the old saying is what goes up must come down, but in physics it's what goes up at the same speed must come down at the same speed if they're landing at the same level. So the idea here is coming back, you're going to have a final velocity of negative 20.1 meters per second. And from these three things, you should be able to figure out the time, and then you can figure out the displacement in the y. So let's see if we can do that. We need an equation, and we typically use the y because if you try and plug x stuff in, you're not going to get a time that's anything of any consequence. But if we use the y stuff, I would say the equation uses VF equals VI plus AT, where VF is negative 20.1, VI is going to be positive 20.1, negative 9.8 is your acceleration, and we're solving for time. So this is actually, your next step is going to be to subtract 20.1 from both sides. And now you're going to end up with negative 40.2, which equals negative 9.8 times t. Divide both sides by 40.2, and you should get divide both sides by negative 9.8, and you should end up with a time that is 4.1 seconds. So that can go here. And now if you've got something going 28 meters per second for 4.1 seconds, that's just V equals d over t. And again, we're calculating for d. So 28.7 meters per second equals d over 4.1. And if you play your cards right, you should get 11.76 meters. D equals 117.6 meters. Can't read my own handwriting. Surprise. 117.6 meters. Moving right along. So, just to recap, the first one is a cliff problem, the second one is a launch problem, the third one is a lab that we did, where we've got that desk, and here's the desk. So it ends up being a cliff problem, but we're going to figure out some other stuff. We know that it's going to land 0.5 meters away from the bottom of the desk, and the desk is 0.7 meters high, so that's actually all we need to know about this situation to figure out how fast it was going, which is what we're looking for. So again, XY chart, VI, VF, AT, D, and again, this is right out of a lab book, or right out of a lab that we did. Remember, X marks the spot. So we're looking for VI. We know because we had a pulse that these two are 0 and negative 9.8. The y initial velocity is going to be 0 because we're not launching it off the desk and we're not rolling it, down off the desk. We're allowing it to come flat straight off the desk. And we also know that it's going to fall negative 0.7 meters. And these three things should be able to give us our time. And then from there we can figure out the initial velocity. Or actually we can also, we know the distance, and that is 0.5 meters away. So a couple of things can happen. We're going to actually use this to find the time, and once we have the time, we're going to be able to use this stuff to find the initial velocity, and that's what we're going to do. So I'm going to say that your best bet is going to be D equals VIT plus 1/2 AT squared to start with the y time, because we can use the y stuff to get time and then plug it back in to get the x velocity. So my displacement is negative 0.7, 0 plus negative 4.9 t squared. We'll divide negative 0.7 by negative 4.9. Negative, calculator turn on, negative 0.7 divided by negative 4.9. That will be 0.142 equal 0.143. equals negative 4.9 t squared. Boy, oh boy. I just did the 4.9. So that will equal t squared, and then you're going to take the square root of both sides. And that will be 0.37 seconds. 0.377, so let's go to 0.38 seconds equals t. So now my time is 0.38 seconds. And now I know v equals d over t for the x stuff. I'm looking for the velocity. I know the distance or the displacement is 0.5 meters. I know the time is 0.38 seconds. 0.5 divided by 0.38 should be 1.31 meters per second. V equals 1.31 meters per second. I hope that helped. 1.315, so 1.32. So I hope that worked for you. Potato cannon, another launch problem. It's going to land 6 seconds after it fired. How fast was it going when it was fired? All right, so now let's make another little triangle here. 40-degree angle above. Pay no attention to the fact that those are arrows. So we don't know how fast it was fired, but it went 40 degrees above the horizontal. And x, y, vi, vf, a, t, d. Again, if you had a pulse, that's 0, that's negative 9.8. We know nothing else except probably the most important thing. The time of flight is 6 seconds. So far, so good. So that means we have to sort of look at a snapshot of this because there's not enough information in the problem for us to look at the whole problem, but we can look at half the problem and look at half of the time. What I mean by that is we launch this thing and 6 seconds later it lands. So halfway through the trip is 3 seconds. Oh. Timer. Halfway through the trip is 3 seconds, and after 3 seconds, we know the final velocity in the y dimension is going to be 0 because it's going to go up and then come to a rest in the y dimension. It's going to keep going in the x, but it's going to come to a rest in the y and then start coming back down. And I've run out of room, but that's sort of the idea of the trajectory of this thing. If we can figure out what's happening in the y dimension, we can figure out what's happening in the x dimension, and we can figure out what's happening for the hypotenuse. So all we need to do is really figure out the VI and the Y, and then we can use trigonometry to figure out the VI in the actual hypotenuse. So, with that said, let's go to work. So I know a final velocity and an acceleration and a time. I'm looking for a VI. So let's use the old VF equals VI plus AT. Final velocity is 0. VI is what we're looking for. A is 3. Time is going to be, I'm so sorry. Oh, I have not had my coffee yet. A is negative 9.8, and time is going to be 3. So negative 9.8 times 3 is going to be negative 29.4. So 0 equals VI plus negative 29.4. Then we're going to add 29.4 to both sides. 29.4 equals VI. So now I know my my YVI is 29.4 meters per second. At this point, you're basically done because you know the sine is the opposite over the hypotenuse. But we know the angle, sine of 40. 40 degrees, 40 degrees. We also now know the opposite side. So let's 29.4. And the thing that we said at the beginning of the year, this is just a number. So sine of 40 is 0.642. And that equals 29.4 over h. Multiply both sides by h, divide both sides by 0.642. So h here, and then divide by 0.642. 0.642. Those go away. 29.4 divided by 0.642. 45.7 meters per second. .8 meters per second. 0.79. So 45.8 meters per second. And I hope you got that. And if you didn't, again, all you have to do is figure out one side of this triangle, and then you can use your trig skills to figure out the hypotenuse using sine, cosine, or tangent. There was enough information here to use the y. We could have also given you enough information to use the x, so just be ready for either. Now we move on to momentum. Momentum here is mv, which is going to be 1200 times 25, really tough, times 25. Momentum of this thing is going to be 30,000 kilogram meters per second. Let's talk about impulse now. Golf ball is struck with a golf club, and anytime we give you a force and a time and a mass, you're generally going to be looking at impulse, which for our equation is, for the equation that we had, F delta T equals M delta V. That's sort of the equation I would go with. And we know we've got a 2,000 Newton force. We've got a time of 0.0015. We know we have a mass of 0.05 kilograms, which is the correct unit, and we're looking for the delta V. And the delta V is the change in the velocity, and if it's sitting on a t to start with, whatever it's going afterwards is our new velocity. So let's just do some little quick math. 2,000 times 0.0015 divided by 0.05, because you're going to divide both sides by 0.05. You're going to have a delta V of 60 meters per second, which means it was going 0, it's now going 60 meters per second. I hope that made sense to you. Parking brake breaks, that's not good, and the vehicle reaches a momentum of 700 kilogram meters per second. What's the velocity of the vehicle? So we know the momentum is 7,800, mass is 1,200, the velocity is what we're looking for. Not rocket science here. Divided by 1,200, velocity is 6.5. Again, we just divided both sides by 1,200. Fair? Next, these are some collisions. So 12,000 kilogram car, railroad car is traveling, and it strikes a 10,000 kilogram car at rest. The cars don't lock together. One of the cars moves forward with a speed of 1 meter per second. What's the other car doing? So this is conservation momentum, where m1v1 plus m2v2 equals m1v1 plus m2v2. And the reason that I'm using this equation instead of the other conservation momentum equation is because we have two cars going in and they don't stick together, so we have two railroad cars coming out. So we've got a 12,000 kilogram car times 2 meters per second plus a 10,000 kilogram car not moving, equaling a 12,000 kilogram car moving plus a 10,000 kilogram car moving at 1. So all I'm doing is taking these words and plugging them into the equation. We're looking for the velocity of 12,000 kilogram car. So 24,000 kilograms, and that goes to 0, equals 12,000 V plus 10,000. We're going to subtract 10,000 from both sides. We're going to have 12,000 V equals 14,000. And divide that, 14,000 divided by 12,000, missing a 0. V should be 1.16 meters per second. and 1.16666, so 1.17 meters per second. I hope that made sense. Let me try and fix this. 1.17 meters per second is my final velocity. So that's good. I hope that made sense. And now we're going to go to another railroad car, and they do stick together. They lock together. And then we can figure out something about the second car. So again, I'm going to use M1V1 plus M2V2 to start, but now M1 plus M2V to end. And the idea here is both cars stick together. So 9,300 times 15 plus some second car at rest, so that all is going to equal 0, equals 9,300 plus M2. How fast are they going after? 6. So 9,300 times 15, it's going to be a big number, 39,500, equals 6 times 9,300, 55,800 plus 6 times M2. And all I did was distribute the 6 over these two things, so now all I have is one variable, that's M2, that I'm solving for. So 139,500 minus 55,800. So I'm going to subtract 55,800 from both sides. I should end up with 83,700 kilogram meters per second equals 6 M2. Divide both sides by 6. So parentheses. And my M2 should be 13,950 kilograms. And I hope that made sense. So perfectly inelastic collision here, normal inelastic collision here, and these are the only collisions we see in real life because there's no such thing as a perfectly elastic collision, because whenever anything collides in the real world, you lose energy. You lose it as sound, you lose it as heat, the shape gets changed in the object, so there's always some amount of energy being lost to the environment. Next question is a bullet being fired from a gun. This is an explosion, so we actually have a perfect inelastic collision going backwards. There's M1 plus M2 times their V becoming M1 V1 plus M2 V2. And the assumption is your initial velocity is going to be 0 at rest. So this whole thing turns to 0. M1 can be the 0.025 kilogram bullet, okay, and that gets shot after the explosion at a speed of 230 meters per second, and the mass of the gun is 0.9 kilograms, and we want to know how fast that's going afterwards. So this is some pretty simple math, but I hope you understand the physics behind it. You know, you have no momentum in the beginning, so you have to have an addition to no momentum at the end. But we have a lot of momentum because the bullet's obviously moving, so the gun has to move in the opposite direction. 0.025 times 230. That's going to be 5.75 plus 0.9b. Subtract 5.75 from both sides. We're going to end up with negative 5.75 equals 0.9b. Divide by 0.9. We should end up with V equaling negative 6.38 meters per second. And that shows the negative being recoil. It means the gun is going backwards. Electrostatics, easy peasy. This was right out of the quiz that we just took. A 560 microcoulomb charge is placed 0.5 meters to the right of a 10 coulomb charge. So let's make 10 coulombs, 0.5 meters. Lights. 560 times 10 to the negative 6, because that's a micro. And the 10 is going to be left alone because there's no micro there. This is a positive charge. This is a positive charge, so we're going to have a repulsion. And then this thing is going to feel a charge that way because we're being repelled. So we're going to use the equation K Q1 Q2 over R squared to figure out the force, and then we can look at what direction it's going in. And we've already established because they're both positive, they're going to go to the right, or this guy's going to go to the right because we're repelling. So K is 9 times 10 to the 9th. Q1 is 10. Q2 is 560 times 10 to the negative 6th, all over 0.5 squared. And if you do the math, you should end up with 2.02 times 10 to the 8th newtons. I just want to verify that. 9E9 times 10 times 560 times 10 to the negative 6th divided by 0.5 squared. So, all right, we just rounded. So this is going to be 2016,000,000 newtons. All right, so either of these, this is going to be in scientific notation rounded. This is going to be what your calculator should spit back at you. And I'd be fine with either of those answers. This was the big question on the quiz, and we have to look at two things. Find the magnitude and direction of the net force on Q3. So Q3 is this one, and we have to figure out what it's feeling from this one, and we have to figure out what it's feeling from this one. So what I've always done is I go for the charge that's furthest away first, and that's going to be F of 1 on 3, the force of Q1, this guy, on Q3, this guy. And that's going to be, again, the big equation is K Q1 Q2 over R squared. So 9 times 10 to the 9th times 5 times negative 8. We were nice enough not to do, oh, I'm sorry. We weren't nice enough not to do micro and milli. So 5 times 10 to the negative 6 times negative 8 times 10 to the negative 6. It's a positive. All over. How far away are they from each other? 18 meters. 18 squared. And if you plug that in correctly, you should end up with 0.0011 newtons. And because they're both, one's positively charged, one's negatively charged, you're actually going to feel a force to the left. Okay, and I know on the answer key it says to the right, and I'm not quite sure why. I think we got that a little bit backwards. So Q3 is attracted to Q1, and if that's the case, it should be going to the left. So this is correct. The answer sheet looks like it's just a little backwards. F2 on 3 is going to be the same deal. 9 times 10 to the 9th times negative, well, now Q1 I guess will be this guy, negative 15 times 10 to the negative 6 times negative 8 times 10 to the negative 6 all over. The distance now is 8 squared, and that should end up being, if you plug that in correctly, 0.0169 newtons. And because both of these are negatively charged, this guy's going to feel a force to the right. So the question is, who wins? Well, this is the bigger number, so it's going to end up going to the right, but not with 0.0169 newtons. We're going to have to subtract them. So 0.0169 newtons minus 0.0011 newtons, because that's what's going to the left, you're going to end up with a 0.0158 newtons to the right for what Q3 is going to feel. I hope that makes sense, and I'm sorry that the answer sheet's a little wonky, but that's what it should be. Negative and negative will feel a repulsion, negative and positive will feel an attraction, but the repulsion is much bigger than the attraction, so we're going to end up with this thing going to the right. Now, easy circuits, and hopefully I can get this done quickly. We know the total voltage is 120 volts. This is a series circuit, so all of the current is going to go through these at the same rate, because there's no choice for them. It's just like a line for I don't know, Space Mountain at Disney World. Whatever's coming out here is going back in there. Nobody can go faster or slower. So in order to figure out the total resistance to get the total current, we have to add the three resistors together. So we know R1 is 5, R2 is 1, and R3 did not get drawn nicely, but 2. So 5 plus 1 plus 2, ohms, ohms, ohms. Last time I checked is 8 ohms. So that's the total resistance. And using V equals IR a whole bunch of times, 120 divided by 8 should give us 15 amps of current. Now, 15 amps of current is going to go through this one, and this one, because again, it's a series. There's no choice for those electrons to go faster or slower. They're all in the same sort of pipe moving together. So they're all going to move at 15 amps. Okay? And at each resistor, we're going to use V equals IR again to figure out the voltage that gets lost at each resistor, and they should add up to 120 volts, because that's how much energy the electrons have leaving. That's how much energy the electrons have to spend as they go through. So 1 is going to be 15I times 5, which is R, times 5. That's going to be 75 volts. 15 times 1 is 15 for V2. And then 15 times 2 is 30 for V3. And 75 plus 15 plus 30 is going to be 120 volts lost in total. So I hope that makes sense. So now we're up to this parallel circuit, and if you remember to calculate total resistance in a parallel piece, it's going to be 1 over R1 plus 1 over R2, yada yada yada, equals 1 over R total. So whatever you get from here, you have to invert to get your new resistance. So in this case, 1 over R1, which is 20, plus 1 over R2, which is 35, gives you 0.078. But if you invert 0.078, 5712, whatever, you will get 1 divided by 0.0785714. You should get 12.7 ohms of resistance. So my R total is 12.7 ohms of resistance. Okay? So I got a 20 and a 35 making 12.7, and that's sort of the big deal. When you have a resistor that's in parallel, it doesn't resist nearly as much. So my total voltage is 120 volts, and no matter what the electron does, it has to lose 120 volts in both R1 and R2. And now we can look at the currents, because that's really what the important thing is. What's happening, how many electrons are going through R2, and how many are going through R1. Well, I know that we're dealing with, I'm just going to erase this to give myself some room. So I hope that parallel math made sense. So I know that I've got 20 ohms and I'm losing 120 volts, so I can use V equals IR to figure out the current going through R1. So 120 equals I times 20 is going to be 6. I know 120 equals I times 35. 20 divided by 35 that is going to be 3.42. And the crazy thing is, 6 plus 3.42 is 9.42, right? Well, the total current, 120, divided by 12.7 equals 9.4. It's coming up as 9.45, but in the area of rounding, good enough. So 9.4 is my current. And you get that, you can get it two ways. One, by adding these two things together, or by doing V equals IR for these two things. So I hope that makes sense. And I also, so the next one, this is the hardest thing that we could throw at you, and we can do this one for fun. But the hardest thing we can throw at you is this guy right here. And it looks like I saved it a little bit from my class, so I'm sorry about that. I wish I could erase it, but I can't. So, first thing we got to do is look at what's happening. So the electron goes through here. So this is series, and then this is parallel. So we have to sort of come up with an equivalent resistance for this parallel piece here, because we don't know too much about what's happening with R2 and R1. But if we do the equivalent resistance of 1 over 10 plus 1 over 5, that's going to be 0.3333. So 1 divided by 10 plus 1 divided by 5, that's going to be 0.3. Not 3 1/3, just 0.3. But then if we invert that, we're going to end up with a resistance here of, give me my pen back, 3 1/3 ohms. So now it's like I've got a series piece and another series piece, and R3 is 50, and this is now 3 1/3. So my total resistance is really 53 1/3 ohms, which means with my voltage of 120 volts, and that's what this all is, I can now figure out what's happening with my total current. And then we can go back and figure out some other stuff. So V equals IR, so 120 divided by 53.3 will give me I, which is 2.25 amps. And now we can say, all right, so in here we're going 2 1/4 amps. So that means I've got 53.3 ohms times 2.25 amps. That will be 119.925 volts. So that's what's happening in this whole circuit. And I'm sorry, I lost track of my thought. Here, all 53.3, I'm sorry, all 2.25 amps are going through here. There's 50 ohms of resistance. V equals IR. I would like to know what the voltage is at 3, but I can figure it out because I know that all 2.25 amps are going through this resistor. So V equals IR, this times this will equal this. 50 times 2.25 equals 112.25. And if I started with 120 and I lost 112.25, what's left to lose in V1 and V2? I don't need this anymore because all I needed that for was to get the total current. So now I'm losing 112.25 volts here, and if I'm an electron, I have to lose the rest here or here, which means I got to lose 7.75 here or 7.75 here, because this plus one of these, which is the only path that it can take, will equal 120 volts. So now I have a voltage, I have a resistance, I can figure out my totals. 7.7, my current, sorry, 7.75 divided by 5, 1.55, 7.75 divided by 10, 0.775, and if you add both of these together, you should get 2.25. 2.32, but rounding just because of how these work. But I hope that makes sense. So this is actually 1.5 and this could be 0.75. But the idea is the same. You know, you're running out of the battery, going through this resistor, losing 112.25 volts. Then you go through this resistor and lose the other 7 3/4, or you go through this resistor and lose the other 7 3/4. Last one. This is kind of fun again. My total voltage again is 120 volts, and I don't know either the total resistance or the total current, but I can figure them out. And the bell's going to ring in a second, so I'm going to pause this. So with 120 total volts, we need to look at what's happening in the rest of this. And I know series, parallel. So instead of worrying about, the best way to attack this is to look at what's going on with the parallel piece and then joining it up with an equivalent resistance. Why won't you work? Equivalent resistance, there we go. And ignore R2, R3, and R4 for a few minutes just until we figure out the total current. So R2 is 10, R3 is 20, R4 is 30 ohms, R2, R3, R4. So if we plug this in, 1 over 10 plus 1 over 20 plus 1 over 30, and then take the inverse of that, we end up with 5.45 repeating ohms of resistance. So this thing is 5.45 ohms. The whole thing here is going to act like one resistor that's 5.45 ohms. You ready for the fun part? We can turn this into a series. 10 plus 5.45 plus 20. So last time I checked, that's 35.45 ohms of resistance for the whole thing. 10 plus 20 is 30, 5.45. So 35.45. Now, we are done with that. The only reason we do that is so we can figure out what's happening with the current and the resistance through this area. Okay? Now we can go back and say, all right, I got 120 volts, 35.45 ohms of resistance, so 120 divided by 35.45 equals 3.38 amps going through this whole thing. Now, here, 3.38 amps, here, 3.38 amps, all through here, 3.38 amps. So I2, I3, and I4 should add up to 3.38 amps. But I1 is 3.38 amps, and I5 is 3.38 amps because there's only one wire going into both of those. These three should add up to 3.38. So now I know V equals IR for these two, which V1 and V5. I can figure out the voltage here and the voltage here. And we're going to lose a little bit in rounding because it's actually 3.38504, whatever. So we're going to end up with ballpark ideas, but it'll be really close. 3.38 times 10 is V1, 33. 33.8, and then V5 is going to be 3.38 times 20, and that is going to be 67.6. Okay, so I'm up to about 100 volts now. That means I'm going to lose a little bit of volts here. So now the issue is, well, I started with 120 volts. I lost 33.8 there at R1. I'm losing 67.6 at R5. So if I'm an electron and I go through this one, I have to lose 18.6 volts. If I go through this one, I have to lose 18.6 volts. And if I go through this one, I have to lose 18.6 volts. Because if I'm an electron, I have to lose all of my volts no matter what path I take. I'm going to lose 33.8 here. I'm going to lose 67.6 here. So 120 minus 33.8 minus 67.6 equals 18.6. And now Mr. Mackinac is going to come on. So I will pause. Announcements are over. So now we've got 18.6 volts all throughout this piece of parallel circuitry. And that's sort of the rule. It's not sort of the rule, that is the rule. Anytime you go through a parallel part of the circuit, you have to lose the same amount of voltage from the beginning of the parallel to the end of the parallel. So all three of these resistors are going to lose 18.6 volts. At this point, come on marker, we can figure out the three currents because we have a V and an R. So 18.6, and we can figure out the I. So 18.6 divided by 10 equals 1.86. 18.6 divided by 20 is going to equal 0.93. And 18.6 divided by 30 is going to be 0.62. And guess what you get if you add this and this and this together? You should get the 3.38 or thereabouts because of rounding of current through all of them. So that's it. I hope this wasn't too terrible for you. This is honestly probably over what's going to be on the final. This is probably over what's on the final. Expect to see a simple parallel circuit and a simple series circuit on the final. So I hope that helped, and you'll also see pretty much one question from everything else that we've done all year, maybe two. So one-dimensional kinematics, two-dimensional kinematics, forces, gravitational force, circular motion, energy, momentum, electrostatics, and now electrocircuits. So I hope this helps. Study like 10% of your grade depends on it, because it does, and I wish you the best of luck.